The objectives of this lesson are pretty simple. We're going to learn how to utilize an operational amplifier, or an op-amp, to increase the signal in a circuit. We're also going to take a short foray into the understanding of analog read versus digital read, because I've talked about how your analog inputs and then you have your digital inputs and outputs, but we haven't really talked about how you would utilize a digital read as opposed to an analog read, and what the difference in the input outputs of those are. And so we're going to do a quick little entry into those concepts. So what you need is breadboards, wires, your microprocessor, all of those of course, but then you also need some resistors. So we're going to start out with a simple 100, 470, and 10 kilo ohms, but you can use similar ones. And then I'm going to use the same photoresistor I used in a previous video. And then you also need an operational amplifier. Mine is a Texas Instrument LM358N, and I like that operational amplifier because it's used in a whole bunch of different schematics on the internet for Arduino, and also you can get a really cheap pack on Amazon of like 100 of them. So that was a great choice for my classroom. Here is the circuit diagram that we're going to follow first. We're going to set up a simple photoresistor voltage drop. So meaning, remember that bit about the voltage divider? The voltage, the 5 volts, is going to come into the photoresistor, and then it's going to go through a resistor all the way to ground. But we're using analogRead, our A0, in order to read the voltage at the point between the photoresistor and the 10 kilo ohm resistor. So set this up on your breadboard, and it is going to look like what you see here. So we're going from 5 volts along this red wire to my photoresistor. From my photoresistor, I can go in 2 directions. One is my analogRead, A0. The other is to my resistor, to ground, ground, back to ground. And so that is how I have it set up. And so what we're going to do here is we're just going to put our finger over it, and we're going to look at the difference between a light on and light off states. We're not doing anything fancy though with the LED like we did before. This is just trying to give us something that we can have a signal that is produced by our device that we can practice amplifying with an operational amplifier. All right, if you haven't done so already, go to my website and download the sketch that you're going to need for this lesson. If you go to the program now, upload your sketch to the device, and then let's look at the serial monitor and look at the values that are being read with our device. So when we put our finger over the device, it drops, and whenever we release, we can see it's low. So let's go ahead and look at the schematic a little bit more. So here we have our circuit diagram where we're going from 5 volts to the photoresistor, and now we're reading right here at this moment with our A0, our voltage divider, and then our 10 kilo ohm resistors are on the bottom of the circuit. And so what we want to do is we want to look and see what an approximate read is, because we don't have an amplifier yet in this circuit. And so let's see what our readings are without an amplifier, and then we can utilize an amplifier and see how these values change. So I'm going to bring the device back over here, and I'm going to look at my values, and it looks like they're about anywhere from 260, 280, 296. I'm seeing a lot. I'm going to approximate that around 280. I'm going to approximate that to be about 280, 281, something like that. Next, I'm going to put my finger over it and put it in dark conditions, and let's see what it approximately is. It is around 85, 86. We're going to go with about 85. So I'm going to write that here for my dark conditions. Next, let's talk about operational amplifiers. This here is a schematic for an op-amp. And so what we have is we have our source voltage, and we have a ground coming off the sides of the operational amplifier. And then we have what's called an inverting input and a non-inverting input. So our negative and our positive, okay? And then the output is here. And so the idea is somehow this circuitry is going to cause either a buffering situation, a gain, a non-gain. There's a couple ways you can hook this up with resistors and such, so that way you're affecting your output based on what is being put into the system. But the idea is the same pattern still apply. Just like here, we knew it was a voltage divider, and we can use that pattern to test the resistance of our photoresistor. We can use an amplifier, but you have to set it up in a certain way in order to get what you're trying to get out of the system. The operational amplifier that I'm using in today's lesson is an LM358N. That's a Texas Instrument operational amplifier. It is this big. Isn't it just adorable? Okay, so at the top of this chip, it is a little half circle, and that half circle allows you to identify the pins. There are 8 pins, and it starts in the top left with 1, 2, 3, 4, and then it comes 5, 6, 7, 8. And so that's how you're able to identify which pin is which. You look up the schematic and it'll tell you this is the schematic. So you have an output for A, an output for B is 7. Your positive source voltage is going to be here, and it's going to come to both of the operational amplifiers inside of this one little box. And then your ground is going to come here to ground 4. And now both of these A and B operational amplifiers have different terminals. You don't have to hook both of them up. You can just use A or just use B. It just depends on what you're trying to achieve. Something else of importance is that you can set up your amplifier as like a non-inverting op amp or a voltage follower. These are the two that I have found myself using the most. And so they're just very helpful. This one, you're just setting it up as a voltage divider where you're coming in from the positive, which remember that is your non-inverting side, and then you're coming out your inverting side, and then you're going to be going one here, one resistor back to the output voltage, and then another resistor down here to ground, which means this point right here is a voltage divider. And that voltage divider is going to allow you to do some math to control your gain, where your gain, which can be abbreviated as AV, is going to be equal to 1 plus R2, whatever your resistor is here, divided by R1 here. And so what's going to happen is based on which resistors you're utilizing in your circuit, you're going to be able to increase your signal or your output voltage here. The other common way I see these operational amplifiers used is a voltage follower. These have a gain of 1, so it kind of just serves as a buffer where you have your input voltage and then it's going to make basically a circle with your output voltage. The idea here is that your output voltage is going to try to adjust itself to equal the input voltage that comes into the system. So these are the ideas and the concepts behind what an operational amplifier is and what it's constructed of, but it's up to you to utilize it in your circuit correctly to achieve the gain that you're interested in getting. So this is how I want us to set up our next circuit diagram. So instead of just coming straight off here to A0, we're going to put an amplifier in this circuit, and we're going to use this non-inverting method where our R2 over R1 is going to tell us our gain. So I'm going to put in R1, I'm going to put a 100 ohm resistor here, and in R2 I'm going to put 470 ohms. That's going to mean that we have an AV1 or a gain of 1 plus 470 over 100 or 5.7. And then we're going to test our circuit, see what our output voltage is, compare it with what we saw previously with no op amp, and see if we truly do have a gain of 5.7 like we're hoping. All right, so let's make some adjustments here. And so our A0 was originally coming to this point here, which is in between our photoresistor. It needs to now come up to our op amp. Where in our op amp? So I'm putting my op amp here. Remember, it goes 1, 2, 3, 4, 5, 6, 7, 8, going this direction. So it needs to go and it needs to read at 1. So I'm going to pull this and I'm going to put it on 1. Okay? But I still need a read. I still need a read point. So I need to put another white one just so I can tell this line is all going to analog in. It needs to come here into this terminal, so number 3. So this one can go to 3. So basically we're going between the photoresistor and the resistor. I need one that's going straight to number 3. And then the 1 point is going to go to my A0. What's next? Okay, so now my 2 needs to take me to a resistor and then another resistor that can come back. So let's go this direction first. So I need to come out of 2 and to some point. Then from that point, I need to go R1 to ground. What was R1 again? R1 was 100 ohms. And so I'm going to take a 100 ohm resistor and I'm going to lead it to ground. So I'm going to go in this same hole with it and then over this direction. Make sure that my wire is nice and snug into my breadboard, and then I'm going to hook a black wire here, and this is going to take me to ground. So now I have gone from 2 to my resistor 1 back to ground. No, I have not. Now I have gone to ground. Make sure you get it in that negative blue. That's going to take me to ground via this wire. Okay? But then it branches. So 2 goes to here, and then it branches and needs to go to R2 next. So I take my next resistor, which is going to be that 470 ohm resistor, and I'm going to put one leg in here with my orange wire that comes off of number 2 of my op amp. And then I'm going to put the next one just in another random spot in the breadboard. here. Okay, keep following it. From R2 now, it needs to go into a 0. So where does it need to go? This A0 came out of 1. So that means I need to connect 1 to my resistor, and I have now done that. So I've gone here to 3, 3, so then 3 is there. Okay, I've done that. 2 comes 1 to resistor and ground, 1 to resistor, back to 1. Okay, so then I have only 2 more terminals left. 4 needs to go to ground. So I can take my pin, put it in there the same side as my 4, and then connect it to ground. I can then do my last one, which is 8. Number 8 needs to connect to power. So where is power? Power is going to be right the same one here as this 5 volts. So I could go here, I could go here. There's lots of places for power. So I'm going to go in here with my 5 volts. And now I have set up my schematic just like I see in my diagram, and I now can test it. Our job is going to be to try and figure out what's our approximate analog read now with our gain. I come back over to my code, make sure I still have my analog read there. I'm going to upload my sketch, and then I'm going to open the serial monitor and see how those values have changed. Alrighty, now I have 676 is high, so I'm going to write that down as my light state. What's going to be in the dark? Whoops, well that might be why it's not so high. I've covered up my pen. Did that change anything? No, it did not. Alright, so now I'm going to cover it. And I'm getting looks like 90, 480, 450. Let's go with like 475. So you can see both of these values have increased. Now I'm going to think though that I might have put too high of a gain, and so instead of seeing an increase in difference, I'm actually going to see both of them having increased. I might have come close to maxing out how much of a gain I could have gotten in the light. All right, next I want us just to change that analog read to a digital read, just to see the difference between an analog and a digital signal. So now you can see ones and zeros. Ones and zeros. Light on is a 1, light off is a 0. And so with a digital, all you're doing is you're saying there's some minimum threshold that must be met in order for it to be considered an on state. And so Arduino has that built in, where it's going to say any values, like a digital or an analog value less than a certain value, is going to be 0. Anything greater than that is a 1. So if you only need zeros and ones, this is great, because now those little variations that you saw, was it 676 or 685? We don't know. You just get ones and zeros. And so you lose a lot of information, but maybe that's better. It depends on your project's requirements. If we repeat this now, but we pull out all of our extra cablings, so we only need now to go into analog here, and we're not using the amplifier anymore. Let's see what our digital code looks like in this case. I put my finger over it. See, there's not enough. I haven't boosted my signal enough for me to get a 1. It's just not high enough. But whenever I add in my amplifier, now I'm getting my ones and my zeros. My ones and my zeros. And that's because I've met whatever that max threshold is for the digital read. All right, let's look at our math and see what our gains look like. So if we compare our light states, we have 676 over about 280. And if I type that into my calculator, then I'm going to get 2.4. For my dark states, I'm comparing a 475 with an 85. And I'm getting 5.59 or 5.6. And so you can see with the light, I didn't get my theoretical gain. It wasn't anywhere near that. But with the dark, I came really, really close. And the reason I think for that is my light, there's only 1,024 pins or voltage integers that I can assign for my input voltage. So in the light, I was getting pretty close to it with my numbers already, so I didn't have the same space that I could have for improvement as I did for dark. So my dark, I was able to see that gain very clearly. And you could definitely do like a percent error equation and calculate how much error is in this measurement.